Hello everyone. So this is the problem solving session of the NPTEL course Functional Analysis, and I'm Pawan Raikwade, PMRFT. So we are in the ninth week of this 12-week course. Okay, so in this session, I'm going to discuss some problems from the assignment so that will help you to solve the problems by your own. Okay, so let's get started. Question number one: which of the following matrices represents an orthogonal projections in R3? Okay, so we have given the three matrices and we have to check which of these three represents orthogonal projections. Okay. First of all, an orthogonal projection in R3 matrix A, because it's again a map from R3 to R3. If I take 3 across the matrix, is an orthogonal projection if A squared is A and adjoint of A is again A. So these are the two conditions we have to check. If these two conditions are satisfied, then that's it. That's the orthogonal projection. Okay. So let's verify with the first one. Okay, so it's a big calculation. So is there any trick we can see? Other things we can also, and for the finite dimensional cases, matrices you can see by maybe eigenvalues and all. Yeah, because which is going to be a square equals a, then the possible eigenvalues are x equals to 0 and x equals to 1. They are the only possible eigenvalues. But in this example, uh, yeah, in this example also 0 and 1 are eigenvalues, so we cannot say anything. This example 2 and 1, 3. Okay, I guess we have to calculate. Or we can, yeah, the second condition, a star equals to a. You can see this condition maybe. Yeah, okay, so first one is not self-adjoint, so this is not orthogonal projection because C1 minus 1. Then the second one, okay, this is self-adjoint, but out of the can we guess some eigenvalue of this matrix? Let's see, 2 minus 1, that's 0, okay, 0. When I evaluate 0, okay, I guess we have to calculate. Okay, so let's just do a squared, which is okay 1 by 9 times this matrix 2 minus 1 times minus 1 2 minus 1 then minus 1 2 again 2 minus 1 minus 1 minus 1 2 minus 1 then minus 1 2. This is just calculations now. Okay, that's the first column. Okay, so 4 plus 1 plus 1 6. Then minus 2 plus, no, that's tough. Okay. First of all, total of 4 plus 1 plus 1, 6. Then minus 2 plus 2, 0 plus 1, I guess. Then this is minus 2 plus 1 minus 1 minus 2. That's minus 3. Minus 2 minus 2 minus 4 and then plus 1. That's minus 3. Okay. So we can just see from, can we see from this entry straight? Because what is the first entry here? 2 to the, okay, let me just verify. 4 plus 1. 4 plus 1 is 5. Then again plus 1 is 6. So first entry is 6 by 9. Okay, so which is just 2. Okay, the first entry is good. Same, 2 by 3. The second entry here, it's coming minus 2. Then again minus 2. Then another plus 1. So minus 4 plus 1 minus 3. It's coming. Okay, I don't know why I read. 1 here. Okay, this is minus 3. Okay, and this entry is again minus 3. This. So this is minus minus plus 1 plus 2 to the 4, then plus 1. 6. This entry is minus minus plus 1 minus 2 minus 2. It is 1 minus 4. That's minus 3. Okay, by far all the entries are going okay. Then this is minus 2. This is plus 1, then minus 2. That's plus 1. Oh, sorry. Minus 4 plus 1. That's minus 3. This entry is minus minus plus 1 minus 2 minus 2 minus 2 again minus 3. This entry is plus 1 plus 1 plus 4 6. Okay, so basically this matrix is again 1 by 3 times. If we divide each entry by 3, there's 2 minus 1 then minus 1 2 minus 1 minus 1 minus 1 2. Yeah, so it's the same matrix, right? Yeah. Okay, so this is an orthogonal projection. Okay. Hmm. Okay, so this is just matrix multiplication. You have to just multiply matrices and see if these two conditions are satisfied. A square equals to a and a star equals to a. I just showed you this. The second option is correct. Third one is also correct, I guess. I mean, you can have a look once, but the second option is also correct. That's also an orthogonal projection. You can see the it's self adjoint. No problem. A star equals a, and when you do a square, it will be again a. Yeah. Okay. So first problem is done. Let's go with the second one. Okay. Which of the following represents an orthogonal projection in L2 minus pi pi? Okay. So the same thing now for even for operators, an operator T defined on Hilbert space. Okay. To a subspace of Hilbert space, I can just write H again. I mean, no problem. You need not go on to. Is okay because it's position. I'll write W where W is subspace of H is called orthogonal projection if same conditions t square is again t and the adjoint of t is t. So these two are the conditions. If these conditions met, then that's an orthogonal projection. Okay, that's all we have to verify. So let's do it. For the option 1, the map is given as t. Okay, all the maps are in L2 minus pi pi. So t is given as tf of t equals to half times ft plus minus t. Okay, for all f belongs to L2 minus pi pi. I mean, then it will imply that t belongs to minus pi pi. Yeah. Now, what will be t square f at t? I can write it as t of tf at t, which is a half times tf at t plus tf at minus t, okay, which is equals to half times tf at t is half ft plus f minus t. Then tf at minus t is half times f minus t plus f minus minus t. That's plus t. If we just calculate this is half times ft plus again ft, so 2 times ft plus half times f minus t plus f minus t, that's 2 times f minus t. So this is just again coming as half times ft plus f minus t. which is Tf at t. So just the calculations, t square is again t. Yeah, because this is happening for all f belongs to L2 of minus pi pi. So t square is t. One condition has been satisfied. Now let's check for the second one. That is t star. We have to calculate is t star equals to t. That's the question. Okay. So let's see what is inner product of Tf and G. Suppose for any G, like let an element G belongs to L2 minus pi pi. So integral, sorry, the inner product of Tf with G is equals to integral minus pi pi Tf at T Gt dt, which is half times Ft plus F minus T G of T dt, which is equals to, you take half common outside, then minus pi to pi Ft Gt plus again half times minus pi to pi F minus T Gt dt. Okay. So so let's just look at this one. If I do the change of variables, let's suppose I put t minus of t is some other will be s. Okay, then this integral here will change to 1 by 2 integral. This will be from pi to minus pi this time. I mean, it looks weird, but it's the symbol, right? Because you have changed the variable from t to minus t in a way. And this is f at s and g at minus s, and dt goes to minus ts. Minus ts, but that's the same as if I take minus outside, then the integral will change from again minus pi to pi f at s g at minus s ds. Yeah, but this is, I mean, no different thing, like you just replace t by s and everything else is same. So I can just write this as integral minus pi to pi ft gt dt plus integral again minus pi to pi ft g minus t dt. Yeah, I mean, this is not going to be changed because s and t, I just replace the variable. So I can just combine it again half times, or integral minus pi to pi ft into half times gt plus g at minus t dt. Yeah, so this implies t star g at t equals to half times gt plus g at minus t, which is same as tg at t for all g belongs to L2 minus pi pi. That means t star is equals to t, which implies t is an orthogonal projection. Okay, that's just easy calculations. So we have verified that the first operator given by here, this is an orthogonal projection. Okay, good. Let's see the second one. Okay, yeah. Second one is okay. What is the second one? TFT. Okay, TFT. TF at T is given by T at FT. Okay. Where is T square? What is T square F at T? This is t of tft is t square ft. So like yeah, this is not the same as pft. Just say that's t squared. So we can directly from implied we can just say that t is not an orthogonal projection. It's basically not a projection. Okay, so B option is wrong, and let's see option number C. It's given by TFT is uh okay. This is not really the subscript. It's in between. It's a product. Okay, ft into characteristic function of 0 to pi t. That's all. C is given as tf at t equals to f at t into characteristic function of 0 to pi at t. Okay, so basically for any f, this is minus pi to pi. So 0 to pi, whatever the ft will be, that's ft. Yeah, and then it is 0. This is the function. Okay, let's see what is t square f at t. Okay, t square f t is can tf at t into characteristic function 0 to pi of tf at t. Okay, and here tf at t is ft into characteristic function 0 to pi at t. Then characteristic function 0 to pi of tf at t. Okay, mm, yeah, okay. So you can just maybe split it like if t belongs to suppose minus pi to 0, whatever characteristic function at t is going to be 0, yeah, which implies t square f at t is going to be 0 when t belongs to minus pi to 0 1. But when t belongs to if t belongs to 0 to pi, yeah, what do we have? We have tf at t equals to ft, correct? From this, yeah, yeah. So okay, we need this to be 1 at t from 0 to pi. That means tf Okay, I don't really see how is this projection. Just give me a minute. Because this can happen, right? That ft, the image of f is not in the interval 0 to pi, in when t belongs to 0 to pi. At that time, this is not going to be ft. Okay. Yeah, okay. So I think there is some problem. I don't know. If my initial guess is that it need not be a projection because in order to get t square, it should be t square is equal to t. We need here as ft. Yeah, for all t belongs to 0 to pi. Yeah, we need that here. For that, what we should know is the image of t in this interval is again in 0 to pi. Then only it's valid, right? Otherwise, it's again will give us 0 because if the image is not in that interval. But for TF, doesn't matter the image where it is, we'll get the image. For example, if we want to think of an example, what about just f of t equals to constant 2 pi? Yeah, for all t belongs to minus pi to pi. So what is TF? TF at t equals to when 0 to pi it's 0 and when uh, sorry, when minus pi to pi it's 0 and when you go from sorry, minus pi to 0 it's 0 and we go from 0 to pi it's 2 pi. But if you do t square f at t, so then it will be 0 when t belongs to minus pi to, okay, no. Yeah, so then this time, okay, this here we have to check. Tf at t into characteristic function of tf at t. Yeah, so if t belongs to minus pi to 0, what do we have? We have tf at t as 0. So this characteristic function will give us 1, but then tf of t is 0 again, so it will be 0, no problem. And then in 0 to pi, okay, we get this characteristic function because tf at t is 2 pi, so it's, yeah, so it's outside of this domain. Yeah, is there any condition on image of the function f? No condition, absolutely no condition. Okay, so if yeah, now this will give me 0 because my TF is outside of this interval, hence this will again be 0. So it will be a constant 0 function, which is not equals to TF. So I don't okay. So I have to check on this question again, and then maybe I'll explain in the next session. But for now, I think it's not a projection. Okay, you can also think about it and maybe correct me if I'm wrong. Okay, let's go to the third question. Let H be a Hilbert space and let P be an orthogonal projection in H. Which of the following statements are true? Okay, first one, norm Px is less equal to norm x for every x. And second one, okay, third one, okay. Okay, it's just an orthogonal projection. So, okay, the third one we can directly say cancel, because if suppose the null space of the orthogonal projection is non-singleton 0, if then there exists x not equal to 0 such that Px is 0, right? That means norm Px will be 0, but norm x is non-zero. So this is wrong. Yeah. Yeah. Now the first and the third you have to check. Okay. Because it's an orthogonal projection, you can always divide the Hilbert space into an orthogonal direct sum of the um, null space of P and range space of P. Yeah. So for any x belongs to Hilbert space, you can write x as u plus v, where u belongs to null space of P, v belongs to range space of. Okay. Maybe this is the orthogonal direct sum. Okay, so what is and whereas this v will be just px, we can write. Okay, so this means what is norm px, which is norm v, and this is anyway, yeah, yeah, because now u and v are orthogonal. What do we know? That norm of u plus v squared is equals to norm u squared plus norm v squared. So you can see norm px squared equal to norm v squared, which is less equal, which is norm of u plus v squared. That is, norm of px squared is less equal norm x squared, which implies norm px is less equal norm x for all x belongs to the Hilbert space H. First one. From this, we can say this implies norm p has to be less equal 1, operator norm of the p. And if you take x belongs to range space of p, I mean, provided that p is a non-zero projection, so that you get a non-zero element, then then uh, what is norm px will be equals to norm x, because for the element in range space p acts as an identity operator. That means norm p is 1. So this third one is again true. Yeah, this was easy. Okay, let's go to the question number 4. Okay, they have given a subspace of R3. Which of the following statements are true? We have to check. Okay. 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 So let Z is this. Okay, Z is basically, you can, if you see, it is just span of the vector. Okay, every element here is X. Okay, I can write maybe 2, 2, 1 span of, I mean, X. If I put Z equals to T, then X equals to Y will be 2 times T, right? So, is it correct? Yeah, 2T, 2T, T. Yeah. So just span of 2, 2, comma 1. Yes, sir. This is Z. So the Z perp will be simply like the perp of this 2 to 1. Yeah, that means the set of all X, Y, Z such that 2X plus 2Y plus Z equals to 0. Just inner product of X, Y, Z with 2 to 1, 0. So this is the second one. Yeah. Okay. The fourth one is settled. And the fifth one. Okay, this fifth. Let G be the space of all f belongs to L202 says that the integral is 0. Okay, which of the following statements are true? C is a closed subspace. Okay, so here Z is a subset of L201, which is a Hilbert space. This we are going to use nicely. Things are very good in Hilbert space. There's a nice inner product. There's a nice representation of every linear functional. Things are good. Okay, so let's see if Z is a closed subspace. Okay, if mm, yeah, if I define the functional phi from L2 to, okay, I'm assuming real valued functions. That's fine, even if complex value. Okay, I'll just write k maybe. Given by phi of f equals to integral. Then you can just verify this phi is a continuous linear functional. And basically, this is just inner product of f with the constant one. I mean, the almost everywhere constant one function. Yeah, this is inner product of this guy. And it's a continuous linear functional, but the Z is just kernel of phi. Yeah, and being a kernel of a continuous linear functional, that's a closed subspace. That's done. First part. Now, second part, Z perp. Yeah. So in any Hilbert space, what do you know is if you take okay, so Z is what here it is, okay, R for any Hilbert space H, let phi is a functional defined by phi of x equals to inner product of x with maybe u for all x belongs to H, where u is just a fixed element in script H. Then kernel phi is just span of u perp, yeah, and yeah, that's all. So here, what is our z? Z is span of the constant one function span, which implies z perp equals to perp because it's a finite dimensional space, so it will be again the same span of singleton one. Yeah, but what is span of singleton one? Yeah. Singleton one means the constant one. Here the constant one is the almost everywhere constant function, constant one function. So when you take span of it, it's just set of all functions which are constant almost everywhere. That's basically what we want. The second option is also true. This is because this set is just span of the constant one function in L2. Then the projection of L2 02 onto Z is given by, okay, so basically, first of all, this when you write like this means this is a scalar quantity multiplied by with the constant one function. Okay, so let's see if that's the projection. Okay, what they are given, f goes to f minus integral. Okay, f minus integral 0 to 2 ft dt into constant one function. Okay, so if this is the projection, then this element should belong to Z, right? So let's see if it belongs to Z. Integral of, so if I write the projection as P, what is integral of PF? Integral of F minus this integral 0 to 2 ft dt into constant 1. Yeah, this is again integral F minus integral F t dt, and this is same here also. This is being a constant, it comes outside, and the integral of the constant 1 in 0 to 2 is 2. This is not 0. Yeah, this is not a projection. So for if you wanted to give a projection, you just should have multiplied this quantity within half here, then it should have been cancelled, and this was a projection. But okay, it's not a projection. This one is wrong. Okay, the fifth one is settled. Let's go to the next one. To be a Hilbert space, we have continuous and symmetric bilinear form. Okay, so that directly defines an inner product. Okay. Yeah, I mean the real inner product. You can verify this. A defines an inner product. So if it defines an inner product, so this quantity is just the Cauchy-Schwarz inequality. And yeah, so you can just see the proof of Cauchy-Schwarz inequality. This proof runs along the exact same line. So just just easy exercise. You can just see it. Proof of Cauchy-Schwarz inequality. And the second thing is x goes to norm x, it defines a norm. Yeah, because this is an inner product, so everything is well defined. No need to check. Just you can see this is an inner product, so everything works well. This defines a norm, and yeah, it works. Yeah, the sixth was just a verification. You can just verify it. And cool. Yeah. Okay. Let H be a Hilbert space. Which of the following statements are true? If xn goes to x in Hilbert space weakly, okay, this is weak convergence. And if norm xn goes to norm x, then xn goes to x. Okay, let's see. Part A. Okay. Okay, what is norm of xn minus x squared? Inner product of xn minus x with xn minus x. This is norm xn squared minus inner product of xn with x minus inner product of x with xn which I can write inner product of xn with x bar then plus norm of x square. Correct? Now, if I define the functional phi from h to r given by phi of x, okay, no x, now here x is fixed, so phi of z suppose, which is inner product of z with x, and this is a continuous linear functional, yeah. So what we know is if, because xn converges to x weakly, that means for every continuous functional, phi of xn goes to phi x, which implies phi of xn converges to phi x, which implies inner product of xn with x converges to inner product of x with x, which is norm x squared. So what is norm xn minus x squared? Here we got, this is okay, you can just say this converges to norm x squared converges to norm xn squared converges to norm x squared by this condition, minus this way xn with x converges to norm x squared again, this again norm x squared, this is already we have norm x squared, so this is 0. So norm of xn minus x converges to 0. Okay, first one is true. Now if you have xn converging to x weakly, yn converging to y weakly, then inner product of xn with yn converging to inner product of x with y. Okay, this seems far-fetched. So okay, let's see the counter example. If you take xn to be the standard vector, suppose en's in maybe L2, okay, and then we know that this en converges weakly to 0, and inner product of en with en is 1, that converges to 1, but yeah, 0 it's 0 it's 0. It's just an easy counterexample, so this is not true. Now the last one, if xn converges to x in norm and yn converges to y weakly, oh, then inner product of x and yn converges to inner product of xy. Okay, let's see. Okay, so part C, what we have is xn converges to x and yn converges to y weakly. Okay. So let's see modulus of inner product of xn with yn minus inner product of x with y. First, a modulus of yn. Okay, I have yn goes to, oh, sorry, not x, here it's y weakly. What should I add and subtract? Okay, so maybe inner product of xn with y plus inner product of xn with y minus inner product of x with y. Let's see what happens. This is equal to modulus of this is inner product of xn with yn minus y plus modulus of place equal inner product of xn minus x with y. Okay, so and by Cauchy law, this is less equal. This is norm xn norm of yn minus y plus xn minus x. That's no y. Yeah, this doesn't help because we don't know about this convergence. Okay, this doesn't help. What about what about x with yn? So I'll be having here xn minus x with yn, and here I'll be having x with yn minus y. So then here I have xn minus x norm, then now yn. Now this is bounded. This converges to 0, and what this guy here? Ah, okay. So for this thing, if you define phi, suppose again from Hilbert space given by 5z as inner product of z with x. Yeah. So phi of yn converges to phi of y, right? Because yn is weakly converging to y. That means inner product of y1 with x converges to inner product of y with x. That is inner product of yn minus y with x converges to 0. Yeah. So yeah, this is the same thing. Inner product of x with y and minus y. I mean, just take the conjugate, but it's the modulus anyways. This guy is also going to 0. So this whole thing is going to 0. Yeah, so it's done. Which implies inner product of xn with yn converges to inner product of x with y. Yeah, good. Okay, so part C is true. That's a good one in Hilbert space. You have one sequence going strongly, one going to weakly, then the inner product goes to the corresponding limit inner product. Yeah, that's good. Okay, now question number 8. Hmm. H be a Hilbert space in which of the following statements are true? The closed unit ball in H is weakly compact. Okay. Okay. So why the inner Hilbert space thing is required for this is, in fact, the first statement is true for any reflexive space. This follows from Banach-Alaoglu theorem. It says that for any Banach space X, the closed unit ball in X dash is compact with respect to weak star topology. Yeah, and the thing here is in reflexive spaces. Yeah, in reflexive spaces, you can identify H with weak topology with H star star with its weak star topology. Okay, because of reflexivity, this works out. Okay, you can just verify this thing. This is a bit just representative. I mean, you have to see it carefully. This follows the weak topology in Hilbert space H. It can be identified with H star star with weak star topology. Okay, asymmetrically. That means, which implies the now since H dash is a Banach space, here we know H dash is a Banach space by Banach-Alaoglu theorem. What do we know? By Banach-Alaoglu theorem, we know that closed unit ball in H star star, I mean, when I say dash, it's star, I mean, it's equivalent here. The closed unit ball in H dash star star is weak, is compact with respect to weak star topology. But I mean, as we have seen from this implies the closed unit ball in H is compact with respect to weak topology. That's it. Closed unit ball in H is weakly compact. So it's just the use of two theorems in a way. One is Banach-Alaoglu, then there is a this is the consequence of reflexivity, that you can identify the space with its weak topology with the its double dual with weak star topology. Okay, yes, that's the trick. Now you know that the closed unit ball in H is weakly compact. The second option is asking whether it's sequentially compact. Yeah, this is the reframe of this question is closed unit ball sequentially compact. But what do we know is from this follows. Answer to this question is yes. Follows from the Eberlin-Schmullian theorem. Okay, some spelling. Schmullian, I guess. You have to check the spelling. Maybe it's wrong. I'm not sure. But from Eberlin-Schmullian's theorem, it says that the weakly compact set in any Banach space is sequential. I mean, a subset of any Banach space is weakly compact if and only if it's weakly sequentially compact. Yeah? This is unit ball is, I mean, not just sequentially compact, it's weakly sequentially compact. Yeah. Okay, so this is true by Emerlin-Schmullian theorem. Now, third part, it asks if every bounded sequence in H has a weakly convergent subsequence, or if and only no. That follows from part B that the separability is a redundant condition. We don't need separability. It's just reflexivity is enough. Yeah. Okay, that's good with 8th question. Now question number 9. Let H be a Hilbert space and let W subset of H be a closed subspace. Define a continuous linear function on W by phi of W equals to the inner product W with U for every W belongs to W. Okay. Then a harmonic extension of phi to H is unique. Yeah, that's okay. And it's given by X2. Okay. Okay, the first thing is we know that Banach, I mean, that's non-preserving extension basically. Are unique if the space is reflexive. Oh, sorry, uh, strictly convex. I mean, it also there follows if it's reflexive because if it means it's strictly convex. Yeah. So yeah, and here the Hilbert space is strictly convex. So the extension is unique, but extension is not given by this function. X question about X with you. Because for example, because U need not belong to the space W. Yeah. For example, if consider your Hilbert space H as R2 and W as the span of 1, 0, that's the x-axis. Yeah, this is your W. And if I define just the constant 0 function on W, which is I can write phi of x equals to inner product of now x means xy basically, or not xy because it's in W x0 with 0 1 element here. Yes, because in this case now in my u is 0, 1, phi is identically 0, but if you consider the phi tilde function from whole R2 to R given by phi tilde of x comma y equals to inner product of xy with 0, 1, then this is not, I mean, norm of phi tilde is non-zero, whereas norm of phi is 0. This is an extension, but it's not an Hahn-Banach extension. Okay, but yeah, so this is not actually the extension is given by the, okay, how do we give, how to give an extension, give the Hahn-Banach extension. What you do is you first take the projection onto that subspace W, okay, then define phi tilde or phi hat from whatever h given by phi tilde of x equals to inner product of x with pu, okay, where u was the function, u was the element, yeah, already you know the u element, this element, okay. So now the claim is phi tilde is the Hahn-Banach extension of phi, okay. Let's see. Hmm. Okay, so first is phi hat is a continuous linear function, no problem. Now what is inner product of like let x belongs to W, what is inner product of x with u minus pu? As you know, because P is an orthogonal projection from H to W, then X minus PU, or sorry, U minus PU belongs to the W perp. This implies this is 0. Inner product of X with for all X belongs to W. That means inner product of X with U is same as inner product of X with PU. Yeah, that means the phi tilde restricted to W is phi. This is an extension, okay, but is it really norm preserving? That's the question right now. Okay, the question is norm phi tilde same as norm phi? Okay, let's see. So what is norm phi? It is supremum over all x belongs to W when x non-zero, norm of phi x upon norm x, correct? Which is equals to supremum of norm of phi x is inner product of x with u. Okay, so norm is it's just modulus here because it's a functional. Inner product of x with u upon norm x, which is same as supremum of modulus of inner product of x with pu upon norm x. But as you know that p is a projection onto W, hence pu again belong to W. So this is just if I put x equals to pu, this is norm pu upon, I mean, squared upon norm pu, which is norm pu. I mean, this is basically less. This was less equal uh, norm pu always, and this is equal because pu belongs to W by because of the projection. What do you know is norm of phi is norm pu, and by Reed representation theorem, you know that norm of phi tilde is also norm pu. So it's settled. Okay. I mean, this is clear, right? Because simply what is modulus of phi x is unit product of x with pu. So by Cauchy sort, this is less equal norm x into norm pu. So this was straight always clear that norm phi is less equal norm pu. It is equal because pu is in w again. So this is a Harmonic extension, and because of the uh, strictly convexity of H, there is a unique harmonic extension. This is the extension. Phi x equals to x with pu. Okay, what do we get as an answer? That this is wrong. This is not a harmonic extension. Yeah, now the B part is you, if u is in W, there exists V non-zero, so that this happens. Actually, this cannot happen because if V belongs to W per, norm of u plus V squared equals to norm u squared by Pythagoras law plus norm V squared, which is strictly greater than norm u squared. So this cannot happen, so this is also wrong. And if u belongs to H minus W, then there exists a u naught, so that phi W equals to inner product of W with u naught for every W belongs to W. Okay. Yeah, so in this case, simply your u naught is just pu. This is correct. Okay, so 9th C. Okay. So question number 10. So almost I have explained every question in this assignment. Okay, so question number 10. If K is subset of R2 closed convex, then PKX denotes the closest point in K to X. Okay. So if K is the closed ball with center origin and radius 2, then PK of X equals to X by 2. For every X belongs to 1, this is wrong because if you take a point X belongs to the closed ball, then PK of X should be equal to X, right? But then this is just absurd. This is wrong. Now K is a straight line given by x1 minus x2 equals to 1. This is the line. This is minus 1, this is plus 1. This is your K, you can say. Then you want the closest point of origin. Yeah, so by basic geometry, this is just the midpoint. Yeah, this is the half minus half. So this is correct. And now the third one, if you take the set K as this part, yeah, and you take any point here, you want to find the minimum, the distance, right? Minimum distance. So like in a way, you want to minimize, okay, distance. If I take any point in this set, X, suppose X comma Y, then you want to minimize X minus X1 squared plus Y minus Y1 squared, right? Where X1 comma Y1 are such that X1 negative and Y1 also strictly negative. So, but then what is x minus x1 squared plus y minus y1 squared? This is just x minus or x plus modulus x1 squared because x1 is negative, so minus minus plus 1 plus y plus modulus of y1 squared. Now you see, for x, you increase, you keep on increasing x, the whole value is going to increase, right? Either x or y, both. This gives you the minimum value when x and y are both 0, otherwise it's going to increase, right? So this is always greater or equal mod x1 squared plus mod y1 squared, which is like 0 minus x1 squared plus 0 minus y1 squared, distance from 0. Yeah, so this is just basic observation that 0 is the closest point for every x1, x2 with which are in this region. Okay, so that's basically every problem of the assignment sheet 9. I hope it's clear. Okay, so let's see you all in the next assignment session. Thank you.